So next up we have James, who's from Georgia Institute of Technology, and is going to be presenting the work on Snail, so single secure iteration localization.
Cool, thank you. So my name is James. I'll be presenting our work on secure localization. So in this work, I'll be talking about specifically visual monocular localization. So visual meaning we're talking about images, monocular meaning there's one, and localization meaning we're trying to find out where an image was taken from, given a map. In the plaintext world, this is usually formulated as a nonlinear least squares optimization problem that's usually solved with gradient descent. And so just to jump to the conclusion, we're interested in introducing privacy guarantees here, and we show that you can do this with secure multi-party computation. It takes about 1 to 10 seconds per image and under 6 gigabytes per image on the data set that we measure. So what do I mean by privacy and localization? So there's two inputs, an image and a map, and then the output is the position of the camera that took the image in the map. So one example of where privacy might be useful, let's say we have a delivery robot, and this robot has a camera. It's taking pictures as it moves to localize itself, but the pictures might contain people's faces. It's navigating these private office buildings, and so they can't be shared. We consider those confidential. But then the map is owned by the building owner, and the building owner doesn't want to give unfettered access of the map to any robot that walks in the door. So we want to design a way for these two parties to interact such that the output after they interact is the position of the robot, but neither has to share their private data. What I just described is the split data setting where the inputs are split between two parties, but we also consider a computation offload setting where for example, say the robot might have both the image and the map, but it seeks to offload the localization computation to more capable resources. So we're not the first to consider privacy and localization. Prior work is obfuscation-based, and given the nature of this work, it's appeared in like computer vision conferences. One example of this work is where they take an image, they extract features out of the image, which are these points, and then they raise the points to lines and solve the localization problem on the lines. Now, unfortunately, this was reversed. It was attacked in a different paper, and the image can be reconstructed from the line cloud. So, by contrast, in this work, we seek to ascribe these privacy guarantees through secure function evaluation. Things like homomorphic encryption or secure multi-party computation. We went with secure MPC, a secure MPC-based protocol that's secure in the semi-honest setting, and I'll give a little bit of intuition as to why that's the case. But first, let me describe a little bit about how localization works, at least in the plaintext world. So like I said, the inputs are this image and a 3D map. Features are extracted from the image, and then they are projected into the 3D map in this gradient descent loop. So there's this projection that takes place, and then the error is measured as being the difference between the projection and the ground truth. And from that, a gradient can be computed, and the pose can be updated. So the image ends up stepping around the map until the error is minimized of these point projections. So a little intuition about why homomorphic encryption is not a good approach to solve this kind of problem. These point projections make heavy use of nonlinear functions like cosine and sine. Computing the gradient requires computing a singular value decomposition, which is a very high depth computation. And it also does not have very many opportunities for SIMD, like single instruction, multiple data. And for all of these reasons, localization is not very friendly to HE schemes, specifically the arithmetic HE schemes like BGV, BFE, CKKS. It's very high depth. It would likely require bootstrapping. The SIMD or lack of SIMD operations means that the packing optimizations of these schemes don't really apply. And so for these reasons, we went with an MPC-based approach. even MPC has a fairly high overhead for people who are familiar with it. Next I'm going to talk a little bit about one challenge we faced when trying to execute localization under MPC. There are some other details in the paper if you're curious, like a performance comparison of two different MPC libraries, how we chose to represent the data. We present a security definition that's tailored for localization, and we also compare two different optimization algorithms, namely Gauss-Newton and Levenberg-Marquardt optimization. But next I'm going to talk about this issue we have with data-dependent control flow. I know the MPC session is running concurrently to this one, so maybe folks aren't as familiar with it. But basically, you can think about it as like a black box. Say two different parties have secret inputs. They want to compute a function, and they each run this protocol. Neither has to share their inputs, but the output is learned by all or a subset of the parties. So as I mentioned before, localization is set up in this gradient descent loop. And one of the biggest problems is that the convergence rate of that loop, or of localization, leaks information about the inputs. It's data dependent. And so if I have an image and it takes me 2 gradient descent steps to localize versus 4, the parties running the protocol learn something about the quality of the inputs. And leaking that, it gives a notion about the difficulty of the geometry of the problem. And that's not something that we can simulate, and it's something we have to fix. Commonly what's done in these settings is a fixed number of iterations is set. In the case of localization, the open source libraries use 20 gradient descent steps before they stop and give up. And maybe that's okay for one image, but if you think about my robot example, this is happening on frames of a video. And so if you look at this over time, there's a lot of wasted work that's happening as the number of iterations is padded out to this upper bound. What we'd really like to do is split the images and only execute the number of steps that we need on each one, the number of gradient descent steps. So what we propose doing in this work is instead of breaking the boundary of our garbled circuit or our secure function evaluation at the boundary of each image, we break it at the boundary of each gradient descent step. And in doing so, it actually hides how many images were used as input for the party who doesn't have the image. At a high level, what we've done here is we've increased the round complexity of the protocol. More of these rounds have to be executed. There's more communication that needs to happen. But the average number of iterations on each image is decreased by a lot. And there's some caveats there that there has to be a stream of images, and there's this lower bound now of gradient descent steps that need to happen. But assuming those are satisfied, there's some improvements that we see. So it's probably not super surprising when you're not doing all this extra work. The runtime of the protocol goes down by a lot. We measured 2 orders of magnitude. In this graph, we're actually looking at 2 different optimization algorithms, Gauss-Newton and Levenberg-Marquardt. I didn't talk about those, but the difference between the 2 sets of lines are when you have to do all of these iterations padded out to 20 versus when you just have to execute what you need, as you would if these were sequential frames in a camera sequence. In summary, this work, we show how to localize on a secret image and map. We draw our security properties from secure function evaluation as opposed to the prior obfuscation-based approaches. It takes about 1 to 10 seconds per image, or 25 to 100 megabytes per feature pair per iteration. That works out to be, in practice, under 6 gigabytes of data. The code's available on GitHub, and we also built a prototype robot in the shape of a snail that actually runs this protocol and drives around. And if you make some reasonable assumptions about what the displacement distance of the robot can be before it needs to relocalize, you find out that it moves just about at the speed of a garden snail. And that's it. Thank you so much.
Any questions for the speaker? You don't want me asking all of them. So, an initial question. You're using gradient descent. Is there any chance you're going to get stuck in local optimas? And if so, like you've reduced the number of steps that you're taking. I mean, doing like simulated annealing is the complete opposite.
Yeah, that's a great question. The convergence properties of this are the same as of the plain text algorithm. So we haven't really modified that too much. That's actually a really important direction of future work. Is like if you're familiar with like crypto nets and the MPC world, like what is that for localization? How can we change localization to be more amenable to these general purpose secure function evaluation techniques? And so, while that's true, actually one of my co-authors, Andre, he has a paper about how do you prove that the output of localization is the minima. And so, maybe those techniques can be applied under some privacy-preserving context.
Good.
Thanks for the talk. You said, so at the moment your prototype is like moving at the speed of a snail. Like, do you see that you could also move much faster, or is like the overhead of the image processing just too slow? And if that's like kind of the bottleneck at the moment, what do you think, like how, in what amount of time is that going to be like feasible for real world application that's fast enough?
Yeah, that's a great question. In this work, we're using the half-gates protocol. There's some improvements to that have happened since we started working on this, and that's in like the MPC domain. And so like a faster protocol from there would kind of apply here. But also, I don't know how realistic it is to expect this kind of thing to work for like AR or autonomous vehicles, things that have really tight timing constraints. We initially were kind of targeting this problem, like an offline problem, where say I have a video from a drone that I took and I want to figure out the flight path of the drone. So that's all run offline. There's not really timing requirements, and so it's less important how long it takes. And then we found we can do it at the speed of a slow-moving robot, which that was a big step for us. But compared to like prior work, the security properties of this approach are much more robust. And so that was kind of first and foremost, and we're hoping the performance will follow.